Hi everybody, welcome back to our next topic here. What we're looking at today are some pretty cool applications of gravitational potential energy, the stuff we've been talking about before. And what we want to look at today is how can we apply those into orbits? You talked a little bit about orbits in grade 9 science. It's some pretty neat things going on there because a lot of the stuff we see, actually just about everything we see in the sky around us is actually orbiting something else. And so it's certainly something that has far-reaching implications. And we're going to start with what an orbit actually is. So our definition for an orbit is given right here. So it's a path in which one body revolves around another, and the only force acting on the bodies are gravity. So an example might be the Earth orbiting the Sun. You can see the picture here. Oops. Yeah, so Earth orbiting the Sun, you might have the Moon orbiting the Earth, those sorts of things. So you have one object orbiting another, going around another, and they're only acted upon by gravity. And again, if you know your history of science, you know that for the longest time, people thought that the Earth was the center of the universe and everything sort of orbited around it. Then some people in the Middle Ages started saying that's probably not the right way to do it. A really important guy for that idea is this guy named Kepler. And so what Kepler actually did in the 1600s, he studied planetary motion, did some really precise measurements, and actually came up with 3 laws that he verified empirically. So what we're going to do is we're going to look at his 3 laws, and then actually what's kind of neat, we can actually apply the physics we know today to these laws that he discovered just by looking at planets and see they make sense. They match up with the physics that we've been talking about. So he's got 3 laws of planetary motion. And so what we're going to talk about to begin with, let's get rid of that, is his first law, aptly enough. So his first law has to do with just what the heck orbits look like. And so he says that each planet moves around the sun in an orbit, which is an ellipse, with the sun at one focus. Now, I don't think you guys have ever mathematically talked about what an ellipse is. It's kind of like a squished circle. But really what defines an ellipse is that the sum of the distance from these 2 points they call focuses or foci is a constant. So as this line, let's say, as this line here becomes shorter, this one becomes longer, but the sum of these two would always be a constant. So anywhere along that path, we'd call that an ellipse. And so again, this was kind of those cool first things that Kepler said that everything's an ellipse. But a special case of an ellipse, if the foci are right on top of each other, is a circle. And since we know lots about circles, let's start with a simpler case of circular motion. And let's try and link our idea of force and circular motion or centripetal motion and see if we can come up with what the heck's going on here. So we'll start with what we know. So we know that the only force involved here is from gravity, and our general form from gravity is this guy here. So this is what we talked about the other day. This is our general form for gravity. But we also know that if an object is undergoing circular motion, the acceleration, centripetal acceleration, is given by this guy. And if the only force acting on us is gravity, we can then further say that the force of gravity is equal to ma. We can set these two expressions equal to each other, and we come up with, oops, too far there, the force of gravity. So G, big M, little m, over r squared is equal to little m v squared over r. And the nice thing here, again, we can actually cancel out a lot of stuff here. So we can cancel out this m with this m, and this r with one of those r's. And we end up with a pretty simple looking expression for speed, g m over r. And again, this is a pretty cool expression. So what this expression actually tells us is the speed of an object in circular motion. So again, so v, this is the speed of an object in orbit. Big G, of course, is the universal gravitational constants. M, this is the mass, and this is important, this is the mass of the body being orbited. So if we're talking about the Earth going around the sun, m would be the mass of the sun, and v would be the speed of the Earth, and r is the center-to-center separation of these two objects. All All right, so again, I think that's a pretty powerful result, that if we look at a speed of an object actually orbiting another one, it doesn't depend on the mass of the object doing the orbiting. It only depends on the mass of the thing that's being orbited. So whether it's the Earth orbiting the sun or like something smaller at the same distance, they'd be traveling at the same speed. Which you can also get from this, as r increases. So notice that if r actually increases, what's going to happen to v? Well, v would have to then decrease. So what does that say? It says the further away you get from the sun, the slower speed should be. And again, I hope that kind of makes sense. If we look at in terms of energy, if it's further away from something, then it's going to have less of an effect on it. And so we'd have to be traveling at a slower speed, since the acceleration should be lower, since Fg equals ma. All right, so there's his first law kind of explored. His second law is actually kind of neat. Again, it comes actually, well, he didn't really understand this idea at the time, but we can understand now that this idea comes from conservation of energy. So what he said was, a straight line joining a planet and the sun sweeps out equal areas in equal space, over equal intervals of time. So what that means again is that as a planet comes closer to the sun, since it's an ellipse, it'll speed up, and as they move further away, it's going to slow down. And this makes sense just from conservation of energy. Because as they're getting further away, their gravitational potential energy is increasing, so their kinetic energy needs to decrease. And as they come closer to the sun, their gravitational potential energy is decreasing, so their speed should be increasing. So this is just, again, a conservation of energy conservation. And we're not going to go through this, but we can actually come up with this nice little expression here that those areas are going to be exactly the same. That's just based on kinematics and this idea that things speed up when they get closer to the sun, so the triangle becomes smaller in width, but longer in length. Because that's the second law. Again, I think that's pretty straightforward, but pretty profound for a guy that only could really look at the sky, didn't know what the heck was going on. And we look at his third law, and this one we're going to spend a little bit of time looking at. So again, to me this is amazing, but he did this just by actually watching the stars and the planets. He had no idea what the heck was really going on in terms of the physics behind it, but he came up with this empirically derived expression that r cubed is proportional to t squared. So what that means is the radius, or the separation of a planet from its star, cubed, is proportional to the square of the period. So what that means is the further away you go, the longer the period, but it's a squared versus cube relationship, not a linear or quadratic or anything nice that you're used to. But again, we can actually trace through these now that we know what's going on with physics, and actually explain a lot of these empirically derived relationships. And we're going to start with two things that hopefully you know. So the first one is just the expression for a period for anything going in a circle, because v is d over t, so speed is distance over time. If we're talking about a circle, in one time period, it would travel once around a circle, which is 2 pi r. So there's the first expression there, and v equals the square root of g mass over r. That's the one we derived on our first law, that the speed is actually just dependent on the mass of the orbited body and the separation between them. So all we have to do here is do some little algebraic manipulation, rearrange these two ideas here. I'm going to take v and put it into, actually not there, put it into there, and end up with this expression here. What the next line is just squaring both sides. So you square both sides here, and you end up with t squared equals this messy jumble over here, which again, just doing some more algebra, some more cleanup, and you end up with actually something that I think is pretty cool. This expression here, which notice is just what Kepler came up with in the 1600s, right there. But now we actually have the proportionality constant. We can say more than just that it's proportional. We know that proportionality constant. And what's really neat about this is if you only have the radius of an object's orbit and the period of its, you can figure out the mass of the thing being orbited. And this is actually how they do a lot of the calculations in astronomy. So for instance, no one can actually weigh Jupiter. You can't put Jupiter on a scale. So what they do is they look at Jupiter's moons. They know how far away Jupiter's moons are from Jupiter. They can do this by looking at measurements, and they can see it. And they look at the period of their motion. And again, so that's how long it takes them to go around Jupiter. So things that are very easy to observe with a telescope. and then doing some pretty simple calculations, you end up with the actual mass of the object or the orbited body, which in this case would be Jupiter. And do the same thing with any sort of planet you can see or any sort of sun you can see. If you know that something's orbiting it, you can get a pretty good measurement of the mass of that object. So I think, if I remember correctly, yes, my first example is based on this idea. So this is, let's say, it's one we want to know to measure the speed or the mass of the sun. So we know that Jupiter orbits the sun at this distance, and it takes 11.9 years to do so. And again, what this means is, with this only the two data, which again, easy to observe from a telescope, you can get the mass of the sun. So let's go through that and do that together. So we're going to start with this expression, which again, that's Kepler's third law. And we're going to rearrange that because we want to know the mass of the sun. So the mass of the sun would then turn out to be 4 pi squared r cubed divided by g t squared. So just rearrange that equation there. I think that's right. Yep, that looks good. Great. And then we're almost ready to plug numbers in. There's one small problem. I hope you can see it. And it's so we have to worry about units. So the radius is in meters. That's fantastic for us. But the problem is the period is in years. That's not so fantastic. Yeah, so anyway, sorry, the period's in years, and so that won't work. We have to put in SI units, which of course is seconds. So hopefully you guys are good with the unit conversion. So I'm going to just jump and tell you that the period for this orbit is 3.75 by 10 to the 8 seconds. So that's how long it takes. And then it's a matter of, again, just shoving those numbers in. And again, I'll leave that to you. But I'm getting the mass of the sun, following this calculation, to be 1.99 times 10 to the power of 30 kilograms. And that's pretty impressive because, again, if you look up the accepted value of the sun, that's pretty much spot on. And I just looked up these numbers here for the distance from the sun and the orbital period from the internet. And so from just that information, we actually figured out the mass of the sun. So again, I think that's a pretty powerful tool we have now at our disposal, thanks to physics. Yay, go physics! So one more example for you here, and we're going to look at Jupiter again. But now we see that Europa is a moon of Jupiter, and it's orbiting Jupiter at a distance of, well, 6.71 by 10 to the power of 8 meters, and I want to know the speed. So I've told you the distance that Europa is from Jupiter. I've told you the mass of Europa and the mass of Jupiter, and we need to know the speed that Europa is traveling around Jupiter. So try to draw a picture here. Here's Jupiter. Europa would be some distance here. The center to center distance I've given you there is, well, that. And then, of course, Europa goes around Jupiter like this. And I want to know how fast is it going. So what is kind of this speed here of Europa? So we think, okay, we have Kepler's 3 laws to kind of help us. We have our ideas of physics. And this actually is going to go back to our Kepler's first law when he just pointed out that objects travel on ellipses, and we're going to assume it's a circle here. So we know that the speed of an object orbiting another one is just given by the square root of gmm over r. But again, this goes back to the idea of which value of mass am I looking for here. So hopefully you're paying attention to the earlier part of the video, and you can see the mass we're looking for here. This mass is the mass of the body being orbited. And so this one wouldn't be the mass of Europa. It's the mass of Jupiter. And r is the distance between them. So that would again be this one right here. Just to drive this home one more time before we put numbers in here, this is really cool because what it tells us is that no matter how much mass Europa has, it would still be orbiting at the same speed. And just going further on to stuff we'll be doing later on, this is really helpful if you're having to deal with orbits and put like satellites in orbit to do things. You don't have to worry about how massive it is. It's still going to travel at the same speed or just dependent on where it is in terms of its height above Earth. All right, so again, now it's just a matter of shoving those numbers in, which I think I can safely leave to you. But when I'm coming up for an answer, and of course, please verify this for me. Make sure you can do this on your own. I'm getting the speed is 13742.9 meters per second. And of course, I've given you, how many digits did I give you? I gave you 3 digits in the question, so your answer should have 3 digits. So 1.37 times 10 to the power of 4 meters per second. So another way to say it is 13 kilometers per second. So if that makes sense. So we're just going to use Kepler's laws here to verify and do some calculations.